All right, so I said we'll be talking today once more about estimators and distribution, because technically when you estimate a parameter, it's not enough. You need to know the distribution of the estimator that you get and how you can use it to either build a confidence interval or make some decisions. So the two things go together. For that, start today by solving a few problems on what we did last time. So this number 4.1.5. So x1 up to xn form a random sample a random sample from a continuous type distribution. Because everything that we are doing now is not in your test 2, it's part of your test 3. Aware of that. You don't do it on the test, but you got to worry about it for the things that are coming, right? Okay. So all the material that is on test 2 is already back in this 2, 3. Chapter 2 and 3. Okay, so, and be very careful with these that we are solving in class 9 for your test 3. The first question is find probability that x1 is less than x2. And basically this problem for me is again for you to train on how to use the conditioning things that we had earlier to find the probability. And then probability that x1 is less than x2. Even if it's even or equal, it doesn't matter actually, because we know that when the distribution graph continues jointly, and we want to find all these probabilities and equals dots, and with probability that x1 is less than or equal to x2, x1 less than or equal to x3, and so on, x1 less than or equal to xn. So we need to find this. Okay. And so I'm going to just do all of that in one. So why? Because there are subcases of, they are all subcases of the last one. So I just write the last one, find the answer, and then you plug in n equals 1, n equals 2, n equals 3, you get the other answer. Okay. So how do we find this probability? Because x1 all the way up to xn is a random sample from the same distribution that is continuous, we can assume that distribution to be something that is not known and then do the work. But technically, the heuristics, when you look at this, would tell you what the final answer should be equal to before you even start working it out. Let's say you have a random sample, none of them has a larger chance than the other one, right? It's random from the same distribution. So they have the same chances of being large, they have the same chances of being small. And you have n of them. What is the chance that a specific one is the smallest one? 1 over n. Common sense tells you that the answer should be 1 over n. So this thing that we want to compute, it should be thinking that should be equal to 1 again. Before you even start working on it. Now let's go through the work. So let f of x be the density of x. X being what the population from which we got the random samples, right? That's the statistics that we do. X is the distribution from which we got our random sample. So they all have the same distribution f of x. Now, the joint distribution of x1, xn is, let me just put here fn of little x1, little x2, all the way to little xn equals the product f of x1, f of x2, f of xn. Why is that? Because we have a random sample from that population. So you obtain the distribution of each of them and you multiply by all the others to get the distribution of the sample due to independent, because a random sample is made of independent observations. Now, if we have the distribution, how do we find the probability that we have here? Just by, what's the formula to get the probability from the density? Integration. So to get this probability here, we need to integrate this function over the set that is written inside here. And over that set, let me call this thing A, okay? I'm denoting this thing A just to not have to write it down again here. So A is equal to the integral. There are several integrals there. There are n of them. Over x1, this thing x2, x1 less than x3, all the way down to x1 less than xn of that function, f of x1, f of x2, f of xn, dxn, dxn minus 1, down to d x2, dx1. How do I compute this integral? There's a reason why I wrote this way. I wrote it this way, ending with x1, because my formula in there is telling me that x1 has to be smaller than every single one of them. So I can fix x1, integrate with respect to everything before integrating with respect to x1, right? So this integral is equal x1 will go from negative infinity to infinity, because it's the one that is less than everybody. I fix it first, then I integrate over it. What about all others? Every other integral that will come inside here will be from x1 to infinity, because all of them are larger than x1, right? So each of them is going to be from x1 to infinity. There is no other condition on x2, x3, x4, all the way up to xn. The only condition is that they are larger than x1. And then you're integrating what that function that is here, f of x1, f of x2, the same f of xn. dxn, dxn minus 1, dx2, dx1. But guess what? When you're integrating inside here, it's the same function. When I integrate this first one, when I want to integrate dxn, everything that is here has no xn, right? The only thing that has xn is this one. So the integral can go all the way to that dxn. And I will have the integral. And it will be a constant for everything else except x1 because it's a function of x1. So it will come out of all the integrals except the first one, right? So that's going to be integral from negative infinity to infinity of this one, what I just said, is what I do here. F of xn, dxn, and everything else stays. Whatever is staying there, guess what? I'm going to apply that same thing to it. So it's going to be integral from x1 to infinity, f of xn minus 1 dxn minus 1, right? It comes out because it has nothing to do with the rest. And it will continue same way all the way down to integral from x1 to infinity of f of x2 dx2. It will come out also. And then what will be left in will be f of x1 dx1, right? Because all those integrals in between, due to independence, have nothing to do with each other. I can get them out of each other, and in the end, it's a product of such integrals. Now, after writing the product, you look at it and you see that this thing is actually same as this, same as that, and they are all equal. All those integrals inside are equal. Because just the variable of integration that is different. It's the same f from x1 to infinity. The same f, from x1 to infinity. The same f from x1 to infinity. So all these integrals are equal. And each of them is just equal to the integral from x1 to infinity of f of t dt, because it doesn't matter how you call the variable of integration. Therefore, this whole thing is equal to integral from negative infinity to infinity of integral from x1 to infinity f of t dt raised to the power n minus 1, because there are n minus 1 such integrals here inside, times f of x1 dx1, which is equal integral from negative infinity to infinity. And what is this integral equal to in terms of the CDF? Can you tell me? The integral that is inside that I'm certain. What is it equal to? Huh? I can't hear you. Well, I said in terms of the CDF, what is it? 1 minus f of x. So that's 1 minus capital F of x, 1, raised to the power n minus 1 times little f of x1 dx1. And I claim that when you do change of variable, no matter what is little f, no matter what is capital F, you do change of variable, this is integral from 0 to 1 of 1 minus u to the power n minus 1 du, where u is equal to capital F of x1. When you do that, du is little f of x1 dx1. And so this here is that. That's u substitution. Get that? So you can see that no matter what is the distribution, if it's continuous, you can actually compute this integral without knowing what that distribution is. Just by doing that u substitution, you get this. And this integral is just a power. So you can compute. So that integral is equal to 1 minus u to the power n minus 1 plus 1. That's power n divided by minus 1 because of the minus 1 that is here times n, right? Power root for integration. And then you plug in 0 and 1. When you plug in 1, you get 0. When you plug in 0, you get minus 1 over n times minus, you get 1 over n. So clearly, we have seen that a is equal to 1 over n. So no matter what is the continuous distribution that you sample observations from, the chance that any of them is the minimum is 1 over n. So for n equals 2, you get probability that x1 is less than or equal to x2, 1/2. N equals 3, you get probability that x1 less than or equal to x2 and x1 less than or equal to x3, or 1/3. That's the answer to the first two parts. First two parts, but find this, find that, and then find this. Now, my interest in this question is actually part B. Do you have any questions on this part? Part B, we say, suppose the sampling continues until x1 is no longer the smallest observation. So x1 less than x2, x1 3, and all the way down to x1 less than x j minus 1, but x1 is larger than xj. That's what the statement means. And we want y equals the number of trials, not including x1, until x1 is no longer the smallest observation. So y equals j minus 1. That's what it means. If you want to count the number of trials until x1 is no longer the smallest observation, and you look at what I wrote here, you do this until x1 is no longer the smallest. So you have j observations. And if you don't count x1, that is j minus 1. That is what the statement is saying. So I just translated that into into a formula. So y is the number of observations until x1 is no longer the smallest one, not counting x1 itself. And if I define that all the way up to j, then it's j minus 1 because I removed the first observation, which is x1. And the question is, show that probability that capital Y equals little y is equal to 1 over y times y plus 1. Y equals 1, 2, 3, and so on, all the way to infinity. Okay, so what ideas do you have on this? How do we answer this? And the hint I give you is it is strongly related to the one we just answered. You see the link between the two things. The answer takes you less than 30 seconds. What's the difference between that set and the previous one? The last one. So how can we manage to make the two look like things that are similar? And remember that here when we are writing this, it's always in terms of events. So this is an event. Yes. Yes. We don't want to integrate again because we have done that already. We don't want to do a work that we have already done. So we want to see something that will make this easier. Just look at it, see that, and then you have your answer. And again, my hint is it's related to what we just did. You don't have to compute the integral. You just need to use that result. And the second thing is, it's the properties of probabilities that we've been studying. What's the link between this set and some sets that will have the form that the other one has? Knowing you just told me, the only difference is the last one. But the game must be played only with what makes the difference, as you mentioned earlier. Yes, that's one. Good. Good. So this event here, if I flip here, if I flip just this, x1 less than or equal to xj, then I'm getting an event of the first kind. But the good news is this event is disjoint with the one that I flip it in. And their union is the previous event, because if I take the union of these two things, it's just this. Right? Because I have all the options for x1. x1 is either less than xj or larger than xj. The probability of that is 1. So the way to answer this question is to say that the event x1 less than x2, x1 less than x3, all the way down to x1 less than xj minus 1 is nothing but the event x1 less than x3, x1 less than xj, x1 less than x, sorry, union x1 less than 2, x1 less than xj x1, but x1 is larger than xj. So the union of these two is that one. Here you're stopping at xj minus 1. And here. So if I know everything up to j minus 1, it is same as knowing everything up to splitting the next one into the two only possible cases. This is the law of total probability that we have. Okay? Because this observation happens under two conditions. Either with the next one being less than xj or the next one being larger than xj. That's the law of total probability. The probability that A, so here, when you take the probability here of x1 less than or equal to x2, x1 less than or equal to xj minus 1 is therefore equal to the probability that x1 less than or equal to x2, x1 less than or equal to xj plus the probability that x1 less than or equal to x2, x1 less than or equal to xj minus 1, x1 larger than xj, because x1 is either less than xj or larger than xj. And this is using the law of total probability that when omega is equal to h1 union h2 with h1 intersection with h2 empty, probability of A is equal to probability of A and h1 plus probability of A and h2. This is what we call the law of total. So if I want A in this problem is that, and then h1 is x1 less than xj, h2 is x1 larger than x2. Am I making sense? All right. So, and this is what we are using. So if that is the case, then this formula here says one over, we computed this earlier, the probability all the way up to xn, we compute and we got that is equal to 1 over n. So if we are finding the probability all the way up to j minus 1, it's 1 over j minus 1, right? Equals this is all the way up to j, so it's 1 over j plus, and then here I call this one b, probability of b. So let's say that probability of b is equal to 1 over k minus 1 minus 1 over j. And this is 1 over k times j minus 1. But probability that y equals little y is what? It is probability that x1 less than x2, x1 less than or equal to xy, and x1 larger than xy plus 1, right? Because x y equal to y means that you have y observations before x1 is not the smallest. So it stops here. And you're not counting x1. That's why it's y plus 1 minus 1. So it's y observation. And that probability is what we just computed. B was for j minus 1. So it's going to be 1 over j minus 1 in this case is the y. So that's y. And j is the y plus 1. And of course, your y is 1, 2, 3, and so on. If it's just the first one, then you have y equals, for x2, you have y equals 1, actually, right? Because you're not counting x1. So when you have x1 and x2, y is 1. That's why it starts at 1. When you have x1, x2, x3, y is 2, because you're not counting x1. So this is what the probability distribution function is equal to. And then 0 elsewhere, because no other value is possible. And the last part of the question is compute the mean and the variance of y if they exist. What do you think? Do they exist? How do I compute the mean in this way, in this case? The formula for expected value of y. The reason why I'm pointing this to you. So that is sum k from 1 to infinity of what? If I call k here times which is the reason why I keep coming back to this is for you guys to figure out that It doesn't matter what I'm calling the random variable in a formula here, but when I'm using it, I've got to use the things that stand there for that random variable. Because it's often an issue, even for those who already get out of this class and figure with A's and be very happy. When you get a problem, you just change the notation and it's done. So you need to know the notations you're putting in here, it's absolutely meaningless. Okay? But as soon as I call it something here, that's what it stands for. And everywhere else, you got to plug in that thing. So here, in this formula of the expected value, K is what stands in this formula as what? And when you want to do this sum, it becomes sum, K from 1 to infinity of 1 over K plus 1. Is this sum finite? No. So this is infinity. So no expected value. I guess you remember the definition of the expected value states that the expected value exists when the integral or the sum of the absolute value times the probability is finite. And if you already compute this one, you got infinity. You can't tell me the expected value is infinity. There's no expected value. And if there is no expected value, obviously there is no variance. Questions? Is there any question on this? Everybody understands it's perfect. We move on. All right, so the new thing that I was to talk about today is basically what we started last time, how to estimate the density when we don't have any information. What we started doing last time was when we do know something up to a parameter, and then we try to do maximum likelihood estimation. So today we want to estimate when we don't know anything, and we find out how to estimate the density. So B for today, non-parametric. And we have two cases that we look at here. Assume for a random variable x, or somewhere you can see a population when you talk about statistics with values. So we know the values A1, A2, down to AM. Consider a random sample. So we take a random sample from that population that has value A1 to AM. A random sample X1, X2, Xn. And then we want to use that random sample to estimate the probability of A1, probability of A2, all the way down to probability of AM. Okay. The estimator of the density or the mass function. The estimator of the mass function is of obtained by estimating of A i's, I equal 1 through m. So if you can estimate all the probabilities, then you say you have a probability, an estimator of the probability mass function. And here, the formula that you can easily use in this case is that the estimator of the probability of each of the AIs is equal to the number of observations that are equal to AI divided by the total number of observations in the sample. Looks funny, obvious. The good news is when you take the expected value of this thing, you find out that it's an unbiased estimator actually of the probability of AI. And there is like a fancy way of writing this is to say that it is 1 over n sum I from 1 to n I sum j, I put I here, but the sum j from 1 through n I j of AI or I doesn't matter how you do call it. So the most important is how you define I of j, where I of A x of xj is equal to 1 if xj is equal to A I, 0 if xj not equal to A. So it's the random variable that counts. All right, this is the indicator function of AI. So anytime you see 1, say you see AI, it says 1. Anytime you see AI, say 1. You don't have AI, 0. And you can show that the sum of these 1s or 0s gives you the number of observations that are equal to AI, because every time one observation is equal to AI, you count 1. And when you add all the 1s, you get the number of observations that is equal to XI. Does this make sense? All right. Everybody? Number of observations equals to here.
No.
Yeah. Here.
Yeah.
By estimate is obtained by estimating probabilities P of AI. That's I equal 1 through M. So each of them you estimate each of them. That's the way of not wanting to write I equal 1, 2, 3, or and dot M. We good? All right. That's it. That's how we will do the clipping for a discrete random variable, and we will say that P of A1 of A2, the hat of AM is estimate. It's the non-parametric estimator because you did not sort of suppose anything on the distribution. There's no parameter involved. Now, in practice, when we have infinitely many values of x, then it is common to set all values larger than a selected A M all equal to A M plus 1. So you just create this fake level where you pull everything that is larger than a certain f, because when you have infinitely many numbers, you cannot see the very large numbers that go to infinity in a given sample. You cannot be sampling and go get observations at infinity. It's impossible. There's no way you can do that. That's the reason why when you fall in a case like that, everything that is larger than a certain threshold that you predetermine, you get all the observations that are above that, you group them to AM plus 1 the next, and you let them be one number. Just use it like that. So let us finish this, and then if we have enough time, go through an example for this and an example for the second one. Otherwise, next time. So for the continuous case, what happens? So observations x1 to xn are from the population x with PF Fx. So, and you want to estimate f hat of x at a given point x. So procedure says, okay, construct intervals one x just, okay, you construct an interval of size 2h centered at x. That is technically x minus h, x plus h. That's what the statement means. We construct an interval of size 2h centered at x, which is x minus h, x plus h. And you define f hat of x for that specific s equals the number of observations that fall within that interval, x minus h, x plus h, divided by 2hn, which in other words could be 1 over 2hn, sum I from 1 to n, I of little x. Where I of little x equals 1 if x minus h is less than xi less than little x plus h, 0 otherwise. So you construct that interval of size 2h that is centered at x, and you count all the observations that fall within that interval. And then you divide by 2hn. And then you could ask yourself the question, why is it that in this case we would proceed differently? Why would what we did for a discrete random variable not work here? And the answer is simple. When we introduced continuous distributions, the first thing I told you was the probability of having a concrete point is equal to 0. So you can hit a specific point. So you can think, you can say what happens when you're close enough to that point. You can estimate that probability, but you can't estimate that chance of hitting that specific point. And the reason why we're dividing by the 2h, n is understandable because it's some n things. We always divide by n. And dividing by 2h is because 2h is the size of that interval. So I take that area and then divide by the area of the thing. See the ratio, and that ratio is going to be a probability. Any questions on this? If you take the size of h0, then you're wasting the time, right? It's based on what I just said. You're bringing it back to the origin. Check the interval. It's open, right? An open interval of size 0 centered at x. Even x will not be in it. And the point is, the good thing about that question is we are actually going towards an h0. But we can't set it equal to 0 because if we make it 0, then we have nothing to work with. So the game in this work, most of the time, and it's an ongoing research actually, people are still working on that topic, finding the best way to choose this, finding the best way to choose that. If you define a target, then based on that target, you know you can find the best way to choose that h to have the best result in your work, right? So, but you need to always know that you are actually looking for a small h. You don't go and take h equal 500, okay? Everything goes in there in 1, you get 1s. So h has to be small. What else has to be? Funny thing about this is when we are just counting the observations here, check this. When we are just counting the observations, is anything that is stopping us from having this count to be very large when we have a large n? It's possible that it's very large. So it's possible that it's actually going to infinity as n is getting large, which is the reason why most of the things we see that we need to control n times h as well, because if n times h is too small, it's also a waste of time. Am I making sense? Okay, so here in this case, II is called rectangular. Yeah, no. This is really statistics that we are starting. So please, if you don't understand something, you make sure you discuss with me. Especially for those who need this for their studies as well. And 2H is called bandwidth. Sometimes it's made a function of n. You can choose h to be a function of n, and then you have a sequence. When you change n, h changes automatically in your code that you're using for the problem that you have. So when you compute these things, you can have a histogram to represent your estimate. The histogram is a bar plot of their both estimators for numbers of observations in each of the intervals. Or for a discrete at each of the points. Okay, so and then all of this will be used. All of this would be useless if we don't see on a concrete example what that means. It just look like Chinese to me, right? That means it would be something difficult because I don't know Chinese. Not that Chinese is not a good language. So here, if everybody is at this page, then let's look at this example that explains what I've been talking about. So you have a data that is simulated from the Poisson distribution. 30 observations, which means x1, x2, all the way up to x30. And it's from a Poisson distribution with mean lambda equal 2. Okay? This table is not pairs. It's the values, the different values. This is x1, x2, x3, x4, x5, all the way up to x30. So these are the sample points that were obtained. How can we use this to estimate the probabilities? These are the estimates. Look at this last guy here. So after 5, that's the hint I was having in a lecture. Everything that is larger than, strictly larger than 5 is combined into larger than or equal to 6 to make one group. Because you cannot graph everything. You cannot have numbers continuously growing and going there when you have a finite sample. It's impossible. Right? So we group all of the observations that are larger than or equal to 6 into one group. Then we estimate. You know that the Poisson has values 0, 1, 2, 3, all the way to infinity. So we need to estimate probability of 0, probability of 1, probability of 2, 3, 4, 5, 6, and so on. But we consider everything after 6 to be 6. And so you go into this table and you count. There are 30 observations. Let's check what is here. It's the number of observations that are equal to 0 divided by 30. Count. How many of them? 1, 2. So this should be 2 over 30. Can you check that? That's what the formula says. Count the number of observations that are equal to AI, divide by the total number of observations. If you check 1 here, 1, you go to the table, you count all the ones. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this is 11 over 30. And so on. That's what stands in this table. And that's how you obtain the estimates. Simple. All right? And now, you use those estimates to get a graph. That graph is called a histogram. And so here you just draw, you start 0, 1, you have bars. This is 0, 1, 2, 3, 4, 5, 6, and so on going. Okay. So around each of them, around each of the numbers centered, as for the continuous, you build a box of size 1. So this is 0.5 to the left. This 0 is here, 0.5 to the left, 0.5 to the right, and 0 is in the middle. And the height of that box is the frequency you had here. It's either the frequency or the probability itself that you estimated here. But when these numbers are too small and you just want to represent the total numbers that you had to divide, this is what this is about. So here, for 0, we had 1, 2. That's why the height is 2. For 1, you also build around, you know, the other one ended at 0.5. For 1, it starts 0.1 all the way up to 1.1. And for 1, we counted how many ones were there? 11. So that's why the height of this is 11. And then you just complete the box around it. Okay? That's what you call a bar plot. You put a bar with midpoint being the point of interest and the height being the number of observations that fall under that one. Does that make sense? All right, so that's what you did here. Have a continuous one. So this example is for a continuous random variable. And you just do the same thing, you estimate, and then you do the plot. The data here is obtained from the normal distribution with mean 50 and variance 100. And you can count how many observations you have. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 times 2, 20. So you have 20 observations. And then it's split here into 6. So it split this into 6 blocks. You can see of 6 blocks of length 10. Okay. That means taking h equal 5. 2 times 5 is 10. And then all the observations after 60, all the observations after 60 are all in one box. Yeah. And so you count them. You count for 10 to 20, for example. You count the observations that are from 10 to 20. How many observations here are there? 1. That's why you have height 1. 2 is here. Height 1. How many observations do you see here that are from 20 to 30? None. That's why you don't see anything. So from 30 to 40, you count. That's what the graph is about. All right. That's it. Any questions about this? So in lectures, it kind of looks difficult, but when you're seeing an example, it's pretty simple what is required from you to estimate it. One exercise that I want to do. 4.1. Exercise. Four point 111. And it says obtain the mean and the bias of the estimator and then the variance. So A, mean and bias of F hat of X. The question itself is already telling you that F hat is not an unbiased estimator, right? But I did tell you that the other T hat was an unbiased estimator, but now you see that F hat itself is not an unbiased estimator. So when we estimate a TMF, we have an unbiased estimator. When we're estimating a TBF, we don't have an unbiased estimator using this method. So how do we find the expected value of F hat of X? It's equal, we use the formula, expected value of 1 over 2HN sum I from 1 through n. And this is the reason why this formula is good, because you see what to work with. If we just write number of observations in the interval divided by, how do you find the expected value of number of observations? Right? But when it's written as sum of I, hey, I know how to handle the expected value of that. And because the random variables are independent, there's no I inside. Because the random variables have the same distribution, all of the expected value gets in, and the expected value of I of X are same because we have the same distribution. So this is equal to 1 over 2HN times n expected value of I1 of X, because they are all equal. Does that make sense? So this is equal to expected value of I1 of X over 2H. And my job now is to show you how to find that expected value. Expected value of I1 of X equals what? That's expected value of indicator function of X minus H less than X1 less than X plus H. How do we find the expected value of the random variable? A discrete one. Sum of what? Variable times probability, right? Do I agree? Now the value of this variable is written here, 0 or 1. 0 here, 1 if we are between X minus H and X plus H. So it is value 1 times probability of this, right? Does that make sense? Okay. So the answer is 1 over 2H probability that X minus H is less than X1 less than X plus H. That's the expected value of this thing, which is nothing but 1 over 2H times F of X plus H minus F of X minus H. And now you see why we actually divided by 2h. This is like the formula of the derivative when you take the limit when h goes to 0, and then you have it centered on both sides. So it's twice the length of the interval is 2h, so you have to divide by 2h. Does that make sense? So in the limit, when h goes to 0, and that's why I was saying we actually need h to be small. When h goes to 0, this formula gives you the derivative of f of x, which is little f of x. So when x goes to 0, this thing converges to little f of x. But what is converging here is the expected value, not the number itself divided by, and that's where the problem is, because if you just take it to 0 and you want to count, you don't see anything. But if you take the expected value, which removes the observations that you're seeing, it's no more those observations, it's their expected values, then your limit and have h going to 0 and you figure what you get. Strange thing there. Any question on that? So this is the mean. There is no, you can't do better. You cannot beat this. And you can see it's not unbiased because in general it's not unbiased because this thing is not equal to little f of x. And so what we call the bias what you call the bias is the expected value of the estimator minus the parameter that you're using that estimator to estimate. When the expected value of theta hat equals theta, we say that we have an unbiased estimator, but when it's not equal, this difference is called the bias. So here you have f hat of x, expected value minus f of x, and the expected value is 1 over 2h, f of x, f of h, minus f of x, and the last part of this question is find variance. As we are running out of time, I'm going to leave you that as something to think about. It's simple, just expected value of the square minus the expected value squared. And you find the expected value of the square the same way we do it. All right. Enough for me today. If you have any questions, feel free to ask. If you don't have, I'll be happy to see you on Wednesday. You don't forget, please, the date of the test and when your homework assignment